Hello and welcome to Mathematics with Simon. I'm Simon. We recently posted a video with the proofs of the compound angle formulae, and Andy Robertshaw spotted that there are some alternative proofs which are very good and interesting, and I posted a video with these in, and then he also has some more improvements. So here's the second version of it. I assume the first version will be deleted at some point. Anyway, these are the, so thank you, Andy, for your contribution in both cases. These are the compound angle formulae for sine, cos, and tan. And so this is the proof of the formula for sine A plus B. So we start with a triangle PQR. We recognise that the area of PQR is a half PQ times PR times the sine of A plus B. This is just a standard formula for the area of a triangle in terms of two sides and the included angle. So using the same formula, the area of PQS is going to be a half PQ times PS times sine A, and the area of PSR is going to be a half PS times PR times sine B. Also, some other observations. PS equals PQ cos A, so PS equals PQ cos A. PS also equals PR cos B, so this side is, it depends which triangle you want to use. You can either call it PQ cos A or PR cos B. And the area of the big triangle is the sum of the areas of the two smaller triangles. So we get that identity there. Now, what we're going to do is we're going to substitute for PS. So in this term, we're going to substitute PS equals PR cos B. And in this term, we're going to substitute PS equals PQ cos A, which gives us this expression. Then we divide through by PQPR, and we get sine A plus B equals sine A cos B plus cos A sine B, which is the answer. Hooray! Now, for completeness, we have to prove that we didn't use the compound angle formulae in any of the assumptions that we used for this proof. Because mathematics is a foundational discipline, so we start with simple truths and then we use logic to prove more complex truths. So this isn't too difficult because you start with a triangle PQR. So what we're going to do is derive this formula for the area of a triangle. Start with PQR, and basically we know the area of a triangle is a half base times height, so it's a half, the base is PR and the height is QS. And then we observe that QS is PQ times sine A, so the area of the triangle is a half PQ times PR times sine A, because what we've done is we've substituted in QS equals PQ sine A into there. So we get a half PQ PR sine A, so we've proved it, and we didn't use the compound angle formula for that. That's fine. Next, we're going to prove the formula for cos A plus B, so we're going to use the cosine law, or the cosine rule, which tells us that QR squared is PQ squared plus PR squared minus 2PQ PR cos A plus B, this angle here. So that's the application of the cosine rule. Also, we've drawn PS as 1 in this diagram. And then what we have done is we have written QR as QS plus SR. It's just a simple substitution. And the next thing we've done is to expand this bracket here. QS squared plus 2QS SR plus SR squared. Now there's some rearrangement. We have added this term, 2PQPR cos A plus B, to both sides. We have taken QS squared and SR squared from both sides. And then what we've done is, by Pythagoras' theorem, we've observed that PQ squared minus QS squared is 1 squared, which is 1. And PR squared minus SR squared is 1 squared, which is also 1. So we've got 2 here. We divide through by 2. We get this expression. We divide through by PQPR, and then we notice that 1 over PQ is cos A. 1 over PR, 1 over PR is cos B. QS over PQ is the sine of A. And SR over PR is the sine of B. So we get our expression cos A plus B equals cos A cos B minus sine A sine B. Hooray! Again, we've got to prove that the cosine rule did not depend on the compound angle formulae. It doesn't. Basically, it depends on Pythagoras. So if we look at this construction here, PS equals PQ cos A. That's just simply using the definition of cos for this right angle triangle here. QS equals PQ sine A. And then we simply got Pythagoras on both of these triangles. So QS squared plus PS squared equals PQ squared. QS squared plus RS squared equals QR squared. So there's two applications of Pythagoras' theorem. Then what we're going to do is we look at PR minus PS squared here, which is basically the same as RS. And so that plus QS squared equals QR squared. So we're just substituting in here for RS. And then we're substituting for PS as PQ cos A. And we're substituting for QS as PQ sine A. And then we're just going to slightly use different notation, because we're going to write PR as C, PQ as B, and we're going to write QR as A, which just makes it slightly neater. We expand this out, we get C squared minus 2BC cos A plus B squared cos squared A, plus from here B squared sine squared A equals A squared. These two terms, because cos squared A plus sine squared A is 1, sine squared A plus cos squared A is 1, this becomes B squared. And we end up with A squared equals B squared plus C squared minus 2BC cos A, which is the cosine rule. Hooray! Okay, so here's another observation of Andy's, which is we can use the fact that sine is an odd function and cos is an even function to help us out here. Tan is also an odd function, because an odd function divided by an even function is always an odd function. Please feel free to offer a proof of that. It's not too difficult. Also, we're not actually proving that sine is odd and cos is even, although proofs are available. I mean, I can think of a proof. If anyone would like to suggest one in the comments, then please do. But anyway, for this video, we're going to assume the true fact that sine is an odd function and cos is an even function. What does it mean to be an odd function? It means that the sine of minus x equals minus the sine of x. To be an even function, it means the cos of minus x equals the cos of x. And since tan is also an odd function, the tan of minus x equals minus the tan of x. Now, how does this come in handy? Because if we start with sine A plus B, the formula for that, we then substitute in minus b for b, and we get this. Sine A minus b equals sine A cos minus b plus cos A sine minus b. The minus sign on the cos sort of disappears because cos is an even function, and the minus sign on the sine passes through. So this gives us the formula for sine A minus b that we recognise. We can do the same thing. We start with cos A plus b, substitute in minus b in place of b. We get cos A cos minus b minus sine A sine minus b, which tells us that cos A minus b equals cos A cos b plus sine A sine b, which is a beautiful fact. Also, tan A plus b, again we're going to put in minus b in place of b, and because tan is an odd function, this tells us that tan A minus tan b over 1 plus tan A tan b is the same as tan A minus b. What fun. I hope you liked this. I loved making it, and I really appreciate the feedback, Andy. Please subscribe and hit the notification bell if you want to see more videos. I'd love to hear your ideas, and most of all, I hope you enjoy your mathematics.